three kind of hypothesis tests that you are expected to know for your upcoming exams. Those being the chi-squared test for independence, which, if we were going to summarize it, is basically asking the question, do these two different categorical pieces of data, do they have any effect on each other? So does one thing affect another? And you can tell what this question is because it's kind of the easiest one to spot, is you'll always have like a little table that has some sort of categories that it's been fallen into. So let's say it was, does gender, let's go with male and female, affect the type of like favorite fruit or something? So you might have something like apple, orange, banana. Okay, so we can spot that one quite easily. So does one thing affect another? Are they independent? Then we have the chi-squared goodness of fit test. So this guiding question is, does the data that I've collected fit a particular distribution? So does the data I have fit a, and I'm going to do dot, dot, dot. We have three different options here. Binomial distribution, or a normal distribution, or what's called a uniform distribution. And we'll go over what those three things are again in a little bit. Then the final hypothesis test that we have is the t-test, and we have one-tailed or two-tailed. And this tests whether the two different sets of data, and it looks at the means and compares them. So does the mean of this data, is it significantly different or bigger or less than another group of data? So does the mean of one group of data, or I should say, is the mean of one group of data statistically significantly different, or it could be less than or more than another set of data? Okay, so the ones that usually people get confused are the chi-squared test for independence and the chi-squared goodness of fit, but I'll talk about some ways of spotting which type of question it is later on. The t-test is a bit more easy to spot, and we'll talk about some ways of checking that out. Now, before we actually do the tests, a quick reminder of our conclusions for the tests. And what we're going to do at the end, we either have one method, we either have the test statistic versus the critical value method, or we can compare the p-value, which is the thing that we calculate, versus the significance level. So if our test statistic, which is the thing that we calculate using our calculator, is less than the critical value, then what we say is that we fail to reject H0. And if our test statistic is bigger than the critical value, then we have to reject our H0, our null hypothesis. I better write that down quickly. So we have H0, what's called our null hypothesis, and you're expected to know what these things, the names of these things are for your exam. And then H1, the alternative hypothesis. Now, the way that I like to remember this is that I just tend to remember, if I can just remember the critical value one, then the p-value and significance levels are just the opposite of the test statistic version. So if my test statistic goes over the critical value, so I think about that word critical. If it goes over, then I can say, oh no, it's gone over the critical value, therefore we have to reject our null hypothesis. So if it goes over the critical value, then we can reject H0. But we can also conclude our test by looking at the p-value of the significance level. So if our p-value, it's just the opposite of what we had before. So if our test statistic is less than critical value, we fail to reject H0. But if our p-value is more than the significance level, then we fail to reject H0. If our test statistic goes over the critical value, so critical, then we reject H0. But if our p-value is less than the significance level, then we would reject our H0. And we'll reference this back when we do the tests individually. So the test that we're going to start off with is we're going to start off by looking at this chi-squared test for independence. So are two variables related or not? Do they have an influence on each other? So the chi-squared test for independence. So usually with a question like this, what we're going to have is we're going to have some sort of table. So this is a good way of spotting this question is by seeing the table. And it's going to ask us to do some, it might reference the chi-squared test. What we don't want to do is get this confused with the chi-squared goodness of fit test. We can tell it's not goodness of fit because we have that table there. Okay, so before we can start the test, we might get asked what our hypotheses are. And this is always the same for all of the chi-squared tests for independence. So H0 is that the two variables are independent. They don't have any relation to each other. It doesn't matter whether you're male or female, like your favorite fruit. It's not based on your gender. And then the alternative would be that they are not independent. Two variables are not independent. So it might be the case that the males really like one particular type of fruit. Therefore, there is a relationship going on between the two variables. I'll give some examples there. So e.g., gender and favorite fruit are not related. And for not independent, gender and favorite fruit are related. Okay, so degrees of freedom. So we might get asked this. Our calculator will tell us what the degrees of freedom are, but we're also expected to know how to show it. And remember, we got that formula. So to work out the degrees of freedom, we do the number of rows minus 1 multiplied by the number of columns minus 1. So we look at this example down here in a second, I'll show you that. And then we'll use this question as a way to go through our method. So we've got a question here. It says a group of adults who either use PC or Mac computers were surveyed. The results are according to their age group and are shown below. So we've got some young people, middle-aged and older. So our first category is age range. And then our other category is whether they use Mac or PC. So type of computer. And we want to see, is there a relationship between these two variables or not? Now, one thing that we've been asked to do is write down the total number of computer users surveyed. Now, sometimes this information is included on the table, but you'll notice that we don't have totals here. So we're going to add these numbers up and figure out what the total number of people were that were asked. Just grab my calculator. So let's add these numbers up. We've got 20 plus 18 plus 25 plus 48, 22 and 37. So in total, 170 people were surveyed. We don't necessarily need to show any working out for that because it's just worth that 1 mark. Okay, so the null hypothesis. Now, I know this is only asking us for the null hypothesis, but I'm going to do both here. So the null hypothesis would be that the type of computer is independent of age group. So there's no relationship between them. And our alternative would be that the type of computer is not independent of age group. So, for example, there might be a lot of people, there might be a load of middle-aged people that use PC, and that might really sway the data. So then it says, using your graphics display calculator, find the chi-squared test statistic. So this is the one where we need that matrix, and I'm going to get my calculator up again. So we're going to add some algebra. No, we're not. We're going to do matrix and vector, and we're going to create a matrix. Now I need 2 rows, but I need 3 columns. And our calculator is going to give me a screen like this. So then I'm going to type those numbers in. So we've got 20, 25, 22, 18, 48, and 37. Enter. And we need to store that. So I am going to store that, and I'm going to store that as matrix A. So if I enter that, and if I type A again, it should return that matrix for me. So it's really important that we do store it, because when in a moment when we do the test, our calculator is going to need to know which matrix to refer to. Okay, so I'm ready to do my test statistic now. I'm going to go to data and statistics. Sorry, I keep pressing the wrong one. We're going to go to statistics, stats tests, and we're going to go to not the goodness of fit, but a chi-squared 2-way test, this option here. So my matrix, it's going to ask me now for the name of my matrix. I called mine A, and then we hit OK. And our calculator is going to return some useful points for us. So what am I going to write down here? I am going to write down the important part of these two. So we have the chi-squared, which is 3.708, or 3.71 to 3 significant figures. And we have our p-value, which is 0.157 to 3 significant figures. So we have to ask, what have they asked? What information has been given here? Well, we've been asked to find the chi-squared statistic, so we've got to write that down there as 3.71. And the critical value they told us is 5.99. This is quite nice because we can conclude in both ways here to show this off. So let's first of all compare our test statistic to the critical value. So 3.71 is less than 5.99. So we've not gone over that critical value. It's not enough evidence here to suggest that we've gone over that critical state. But it's nice here because we also have the p-value. So because we're doing this at the 5% significance level, 5%, remember, is the same as 0.05. We could also conclude this by saying 0.157 is more than 0.05. Now, what situations have we got here? Let's have a look. So our test statistic is less than the critical value, and our p-value is more than the significance level. So our conclusion is as follows. We're going to say there's not enough evidence to reject H0. So what does that mean for our test? Well, it means that there's not enough statistical evidence to say that they are not independent. So it looks like, losing this data, that the type of computer is not related at all to the age category that people are in. So we can say that they are independent. Okay, and that's the chi-squared test for independence. So we'll quickly go over some key things. So we've got to remember, our null hypothesis is always that they are independent. Our alternative is that they are not independent. Degrees of freedom, we need to know how to calculate it. So for this one, we've got 3 rows. So 3 minus 1 times 2 minus 1. So 2 times 1 is 2. And we can check, actually, does our calculator show us the same thing? It should tell us what the degrees of freedom are. It does. So df there is 2. So we know we're right. We found the test statistic. And for this one, we actually had both pieces of information. So we could include it one way, both ways. Now, in the exam, you only need to do one of these. And sometimes you are forced to use one of them. And then we do a little conclusion at the end. There's not enough evidence to reject the null hypothesis, so the computer and age are independent. Okay, so that's our first statistical test. We're going to move on now to the t-test. So the t-test, there are 3 different, well, 2 main different t-tests. One of them has kind of 2 variations, but they compare the means of 2 different sets of data and sees whether or not they are statistically different, or if one of them is statistically more than the other, or if one of them is statistically less than the other. So we're going to go through. We're going to start off with the two-tailed test. Now, for the two-tailed test, it's called two-tailed because we just want to see if the 2 sets of data have different means. We're not interested in looking at whether one mean is more than the other or whether one mean is less than the other. We just want to see if there's any significant difference between the 2 different means. Now, for a two-tailed test, our hypotheses are always going to be as follows. Now, you always write these in terms of mu1 and mu2. So for our first t-test, the two-tailed, we're going to say, well, our null hypothesis, the status quo, if you like, is that the means are just the same. There is no difference between the means of the 2 groups. And our alternative hypothesis, because we're looking to see if there's a difference, then our alternative hypothesis is that the means are not the same as each other. And this is enough for us to get the marks in the exam. We don't have to overcomplicate this. We don't need to write it in words. That is enough for us to get the marks here. Okay, so we can see this nice table. This is always a big clue that we've got a t-test question when you've got 2 rows of data like this. One key part of the t-test is that your 2 groups do not have to have the same amount of pieces of data in them. So we can look out for that as well. Let's read this question. So a music producer wonders how the average duration of songs has changed from 2010 to 2020. To compare the average length, he takes a random sample of the most popular songs in 2010 and 2020 And the following data shows the data in seconds for the two samples. The producer is interested to see whether the mean length of the songs in these two groups is significantly different. So this sentence here is telling us that it is a two-tailed test. It doesn't say that he thinks one of the groups is more than the other, or if one of the groups is less than the other, just that they're different. And if we see that word different, then we know it is a two-tailed test. Okay, so state the null hypothesis. We're doing this 5% level of significance. A t-test was used. I'm going to state the null hypothesis and the alternative, and that's going to be the same as what we've done up here. So I've already done that. The null hypothesis is that the means are the same, and the alternative is that they are different. So determine the p-value for this test. Okay, so what we're going to need to do is we're going to need to go to our calculators now. And we need to add in a spreadsheet. And we're going to start off by labeling these at the top. So you choose what to label them. I'm going to go with A and B, just to keep it nice and simple. So A for this first one. Oh, doesn't like that. Okay. Come on, let me give it the letter A. It's because I've got something else called A. Okay, so we're going to go with B and C then. This is important so that when we do our test later on, our calculator knows which columns to look for. And then we need to input our data. So I'm going to go through and put in this data to 218. And my other column, it's important to take your time here because even if one of these numbers is wrong, then it could change the result of our test. And 214. Okay, so all my data is in there now. I can go back to, you can do it in the spreadsheet, but I prefer to go back to the just regular calculator to do my calculations. And we are going to go and find our stat test. So menu, statistics, stats tests, and we're looking for the t-test. Okay, so two sample t-test, not t-test, not two sample z-test, two sample t-test. Now, my data input method is data. Okay, so for my list one, I called it B. And my list two was called C. I'm not going to change the frequencies, but the hypothesis, this is the really important part. I need to decide, am I doing a one-tailed or a two-tailed test? So I know I'm doing a two-tailed test. So I'm going to choose the alternative hypothesis that matches with my question. So we're not equal. The means are not equal. Called is always no, and we can hit OK. All right, and it's going to return our results. So we are specifically looking for the p-value here. So I'm going to write this down. The p-value is 0.0504 to three significant figures. And then I need to state and justify the conclusion of my test. So because we only have the p-value here, we're going to have to use our conclusion with the significance level. So let's compare it. We are doing this to a 5% level of significance. So 0.0504. Well, that is bigger than 0.05. So again, we're not underneath that significance level. So there's not enough evidence here to reject that null hypothesis. So our conclusion, there's not enough evidence to reject H0. So what does that mean in our context? Well, it means that the means of the group, the mean song length, are not song lengths are not statistically different. And that's kind of the basics of a t-test. So I hypotheses, we do the test, usually with comparing the p-value with the significance level with your conclusion. So that's the two-tailed. Are they different? Let's look at the one-tailed. So one-tailed, we have two different options. We might think that the first group and the second group, that the second group has a bigger mean than the second one, the first group. Or we might think that the mean of the second group is actually less than the first group. So depending on the wording of the question will depend on whether or not we're doing it, the second group is bigger or smaller. So we're going to look through this question here and try and decide whether this is, well, we know it's going to be a one-tailed, but why is it one-tailed? So there's a company that's making lithium-ion batteries. They believe that their new ARC technology, so they believe that it's improved the life of their batteries. So they think that this new battery is going to have a longer battery life. So they test it with 8 of their old batteries and 8 of their new batteries, and we've got that in the table. They wish to determine whether there is any evidence that the new batteries have a longer time to failure than the original batteries. Key word there, longer. They believe that the new group is more. Okay, it follows a normal distribution with the same variance. Okay, that's important. That's an assumption of the t-test. Let's write it down on our hypotheses. Okay, so the status quo, H0, the null hypothesis, is that the means, we can use LA if we want to, or can we just use mu1? It's always that they are the same. But our alternative hypothesis this time is we need to decide which way around our inequality is going. Well, they believe that the new group has a longer battery life. So you would expect that the mean of the group is higher than the mean of the first group. Okay, so like before, we're going to go to our calculator and put this data in. You can do that at the same time as me. And I'm going to go back to my spreadsheet. If you want to start a new document here, that's fine. Or we can just use the next columns and make sure that we label them in an appropriate way. So I'm going to use L and A like they do. So L and, I can't use A. So let's go lithium ion batteries. Let's go old and new. So old and new batteries. And type this in your calculator. So 43.6. 36.2. Take your time. If one of these goes wrong, then it will throw off your results. Okay. Second group of data. Uh, 48.1 and 35.3. Okay, so back to my calculator. Because I've got different labels, I can just use the same calculator I had open before. And we're going to go back to our stats test. So statistics, stats tests, a 2-sample t-test, and we are inputting data. So our list one, I went with old, I'll choose it from the list, and new. Okay, so frequency stays the same, but we are going to change that alternative hypothesis so that it matches exactly the alternative hypothesis that we wrote down. So we need to make sure that we're choosing, we think that the new mean is bigger than the old mean? Board is no, and we can hit OK. Okay, so we're looking for the p-value. Slide that over. Our p-value is 0.0741 to three significant figures. And then we can conclude our test. What level are we doing it to? We're doing it to 5%. And 0.0741 is bigger than 0.05. So let's check. The p-value is bigger than the significance level. So again, we're going to fail to reject H0. So the new batteries do not have a longer battery life. Now, if you want to use this resource in the future, I have put in the little mark scheme here. So if you just zoom in, you should be able to see the marks and what you would get for each part of that question. Okay, so that's the one-tailed test. It's one of the groups is going to be bigger than the other. So we've done that the second group is bigger. Let's see if we can do one where we think that the second group is going to be smaller. So let's see if we can spot that in this question. So we've got a pharmaceutical company. They've got a new drug in which they claim can lower blood sugar levels. Okay, so there's that clue. They think that the second group is going to be lower. They want to test a claim. She starts this by splitting the group of diabetes patients into two groups. So the people in group B were given the new drug, and we've got the data in the table below. So we're doing a two-sample t-test, 10% level this time, to decide if the new drug is better at reducing blood sugar levels. Okay, so they even bold in this question to say that the second group has got to have a lower mean than the first group. Okay, so they get given the null hypothesis here. And we then want to just write down the alternative hypothesis for the test. So the first one is that mu A is the same as mu B. Let's use A and B this time. You wouldn't get marked down for writing 1 and 2. Now, what's going on? This drug is going to reduce the levels. So this second mean is going to be less than the first mean. Okay, so just like the other two, we're going to go to our calculators now. You can get started on this whilst I'll do the same. Okay, and if you want to, we can still do this in our same spreadsheet as before. We just need to choose new labels. So we're going to do old drug and new drug. Oh, I'm running out of letters here. Let's go with new drug and old drug. Let's just go with two letters that are next door to each other. So let's go with G and H. I might recommend like doing a new spreadsheet just so that you can use new labels. It's up to you. You just got to know which labels you're using. Okay, let me get my data. Okay, so 17. First group, second group. Okay, let me take a quick note of my letters again. I did G and H. So back to my calculator. And we're going to do statistics, stats test, two-sample t-test, data, G and H, G and H. And we need to change that alternative hypothesis again. So what is my alternative hypothesis? I believe that the new group is going to have a lower mean than the first group, and then I can hit OK. Let's get that p-value. Okay, so my p-value is 0.115 to 3 significant figures. And this time we're doing it at 10% significant level. So 10% is going to be 0.1. And 0.115 is bigger than 0.1. So like the other two that we've done so far, there's not enough evidence here to reject that null hypothesis. If we go back to our thing up here, our p-value is bigger than the significance level. It's not gone under that significance level. So there is not enough evidence to reject H0. So what does that mean in that context? Well, it means that that new drug has not really lowered the blood sugar levels. It's just kept it the same. So the new drug is not more effective. Okay, so that's our t-test. So to summarize, we've got, on the t-test, we've got a two-tailed test with these hypotheses so that they're the same and that they're different. Or we have a one-tailed test where we might think that the second group has got a bigger mean, or we might think that the second group has got a smaller mean. You just got to really look at those words that are in the question, like longer, or they think that the drug is better at reducing, to decide which way around your hypotheses are. Okay, so there are chi-squared test and t-test. Let's move on to our chi-squared, the last ones now. The chi-squared goodness of fit. So this is where we have some data, and we have a suspicion that this data might follow a particular distribution. So the three distributions that we have are a uniform distribution, the binomial distribution, and the normal distribution. Now, there are some key things here. What we're going to be doing is we're going to be comparing our observed values, so what we see, the data that's given to us, versus what we would expect to see if that distribution were the one that we thought it was going to be. Now, a key formula here is the expected result formula, because we're going to be comparing expected values. So this is one that's kind of in the formula booklet, where if you want to work out the expected number of things that would happen if you know a probability and then total number of trials, you take the total number of pieces of data. So let's say I surveyed 100 people. I would take 100 and then multiply it by the probability of that event happening. Now, this is more for the normal and binomial, because for uniform, we're going to do something slightly different. All right, so let's do uniform first. Now, what is a uniform distribution? This is where all of the values are spread equally between the different categories. So, for example, this is about the number of customers visiting a dry cleaning store. If it were uniform, then all the values are equal for each. Could be day, it could be, what else have we got? It could be, I'm trying to think. Day of the week, it could be months of the year, it could be years. For each, let's say each category. So they are all the same, all the values are equal. All right, so what we're going to need is we're going to need some observed values, and we're going to need some expected values. And for a uniform distribution, the expected value will be just that each of the slots, days of the week example, is the same number. So let's read through this question. We've got a dry cleaning store. It's open 6 days a week and closed on Sunday. The manager of the store forms a model to forecast the number of customers visiting the store so that he can effectively roster the staff. Okay, so according to his model, customers visiting the store are supposed to be evenly distributed across the 6 operating days of the week. So there's that kind of trigger sentence, the key sentence. He thinks that they should be evenly distributed. So evenly distributed is our clue that we think it's going to be a uniform distribution. Okay, so the manager conducts a chi-squared goodness of fit test at a 5% significance level, and his hypotheses are as follows. Now, I really like this question because these hypotheses here are going to be the same for the rest of our tests, for the binomial and the normal as well. So the null is always that the data follows the model, and I'm going to write this up here. The data follows the model. That could be uniform, normal, or binomial. And then the alternative is that it just doesn't do that. So H1, the data does not follow the model. Okay, so we've already got that for our uniform distribution. And we're going to have to say, determine the expected number of customers visiting the store each operating day according to the model. Okay, so I'm going to need my calculator here. That's not what I wanted to do. I wanted to do a split view. Okay, so let's ask ourselves. So we don't know how many visitors there are in total. So that's probably the first thing that we're going to need to figure out is if they were evenly spread across the 6 days, well then how many would we have in each group? So we're going to need to add these up. 134 plus 146, 127, 133, 111, and 153. So the total we've got is 804. So I'm going to write down what I did there. So 134, 146, 127, plus 133, plus 111, plus 153. So we've got 804 people in total. And if they were evenly spread across the 6 days, then we would expect how many people on each day? So divided by 6, we would see 134 people on each day. This is our expected result. Okay, so the number of degrees of freedom for this test. So degrees of freedom is always one less than the number of pieces of data that you have. So for us, we've got 6 days. So 6 minus 1 is 5. There's 5 degrees of freedom. It's always one less than the number of pieces of data that you have. Okay, so write down the conclusion to your test justifying your answer. So for all of these questions, I am actually going to start a new document now because my calculator is getting a bit full. And we need to add in a list and spreadsheets. So what we want here is we want observed versus expected. And observed always goes first. So we want, I'm going to give this a name of observed and expected. And what we want in the first column is what we observe. So we observe these numbers that were given to us. 134, 146, 127, 133, 111, and 153. And what we would expect, if this followed a uniform distribution, is we've shown that we would expect 134 people on each day. So we type 134 for all of these. So we've got our observed versus the expected. Okay, so we need to add a calculator in now. We're ready for our test. So we're going to go to statistics, stats tests, and we're looking for chi-squared goodness of fit. And it's going to ask us for our observed list. So I called this O, and my expected list, E. And the degrees of freedom, well, we worked out that we've got 5 degrees of freedom. So we'll type that in 5. I'm hoping that this time we're going to get something that has, maybe we get to reject H0, but let's see. Okay, so we've got our results. We're going to write them down. And we've got our p-value is 0.151 to 3 significant figures. We also have the chi-squared statistic, which is 8.09 to 3 significant figures. But because we don't have the critical value here, we can't compare this one. We're going to have to do the p-value with the significance level. Okay, so we've got 0.151. We're doing a 5% level, and that is definitely bigger than 0.05. Oh, we've ended up with another one, haven't we? So this is go back into our little table from earlier. The p-value is still more than the significance level. So there's not enough evidence to reject H0. So what does that mean for our result? We'll go back to our hypotheses, is that the data follows the model. The data does follow a uniform distribution. Now, if you were to get a chi-squared goodness of fit, I would probably say that this might not be the case, but a uniform distribution question is kind of the type of question that would come up on paper 1. It can be a shorter question. And then normal and binomial tend to be a little bit longer because they require you to work more things out. Okay, but it's going to follow the same principles. Right, so let's look at normal distribution. The guiding question here is, does my data follow a normal distribution? Okay, so just a quick reminder of normal notation. We might have a variable x that's distributed normally, and then we're going to have the mean, and then the standard deviation squared. So just a quick reminder, this is the mean, and sigma on its own is the standard deviation, and sigma squared is what we call the variance. You're not often asked about the variance, but it's important that you know that standard deviation is just the sigma, not the number squared. Okay, so we're going to need, like we did before, some observed and expected. And this question often starts out with us calculating some things with the normal distribution. Right, so we have got a tennis ball manufactured by Wilson Sports have to meet regulations in order to be approved for tournament play. During the test, balls are dropped from a height of 254 centimeters on a granite surface. The height of the first bounce are assumed to follow a normal distribution. So let's call it x. The height of the first bounce And we've been told that it follows a normal distribution with a mean of 140.6 and a standard deviation of 2.8. And then what it's going to do is it's going to help us out with these questions. So first of all, we want to find some probabilities that it's less than 135 and more than 145 centimeters. So I would recommend that you do a little bit of sketch when you're doing this, because it shows you that you know what you're talking about. And we'll remember that the normal has that nice bell curve shape. It's a little bit tricky for me to do on here. It's symmetrical around that mean of 140.6. And we want to work out what's the probability that a ball bounces less than 135 centimeters. We want to work out this area here. Okay, so we're going to use that doing with our calculator. Right, so we just need to be in the normal calculator, and we're going to do to statistics, and we're going to go to distributions this time. Normal, we want to do normal CDF. So C standing for like cumulative. We want it's less than 135. So normal CDF. So our lower bound is going to be something really, really small because we want to start all the way as close to 0 as possible in this direction. Our upper bound, we want to go up to 135. And our mean is 140.6. And our standard deviation, we were told, was 2.8, not 2.8 squared. Okay, lovely. So we've got that first result. So what is the probability? We can write it like this. The probability that x is less than 135 is equal to 0.02275. Let's round that 228, three significant figures. And then we want to do more than 145. Okay, so let's do another little sketch here. So more than 145 is going to look something like this. Same sketch to begin with. 140.6. What's the probability of it being more than 145? Well, we want to know what this area is this time. So similar thing to before. Bring my calculator back up. And statistics. Distributions, null CDF. Okay, but now this time my lower bound is 145. And my upper bound is going to be a number that's really, really big. I want to go as close to positive infinity as possible. So we want to go all the way up to the end. So I'm just going to type in a big number, lots of nines. This is 140.6. And this was 2.8. To enter, see what we get. Okay, so the probability that it's more than 145 is going to be that number there. Let's write that down. Now, usually what they're doing here is they're trying to get you to do part of the question that will come up later on at the beginning and gain some marks. So more than 145 is 0.0580 to three significant figures. Okay, so that's just standard normal. That could be asked somewhere else in the paper as well. We haven't actually gotten to the goodness of Fitbit yet. Okay, so let's see what we've got. An inspector selects 800 tennis balls at random for the bounce test. The height of each bounce ball is measured and recorded. Find, correct to one decimal place, the expected number of balls that bounce between 135 to 140 and 140 to 145 centimeters. Okay, so we're going to need to use that expected value formula. So the expected value formula is the amount of times that we do something. So here, 800, multiplied by the probability of each thing happening. Now we know the probability less than 135 and more than 145, but we don't actually have the probability that a ball will bounce between these things yet. So let's work those out as well. So the probability that a ball bounces between 135 and 140. So back to our calculator, and we also want to know the probability that it's between 140 and 145. Okay, so I'm going to write both of these things down so that I can do them in one go. My calculator again, and we're going to go to statistics, distributions, normal CDF. Now this time, my lower bound is 135, and my upper bound is going to be 140. 135, 140, 140.6, and 2.8. Just double check, it was 2.8. Yes. Okay, so there's my probability. I've got between 130 and 140, 135 and 140, 0.058. Oh, no, that's not true. 0.392. And then we've got one more time that we need to do it. Statistics, distributions, normal CDF. Lower bound is going to be 140 this time. 145 upper. 140.6. And 2.8. And we've got our last probability. So 0.527. Okay, so we've got our probabilities. In our formula here, we just worked out these things. Now, to find out the expected number of balls, we need to take our 800 and multiply that by both of these. So 800 multiplied by 0.392 and 800 multiplied by 0.527. That will work out the expected number of balls that bounce between those two heights. Okay, back to my calculator. Now, the best way to do this would be to do this as you were going along. So if I take this answer here, can I paste it and multiply that by 800? So I would expect 314 between 135 and 140. I'm going to round that up, 314. And then if I take my second probability and multiply that one by 800 as well, that's going to give me how many I would expect between those values. So 421. Okay, so let's see where we are and what we've got to do next. Right, so we've got the actual recorded bounce heights are shown in the following table. So this is our observed values. They're going to do a chi-squared goodness of fit test to see whether or not this data here follows a normal distribution. So in words, what are our null and hypothesis tests? So H0. And just like the uniform distribution, it's going to be that it follows the distribution. So the data follows a normal distribution. With a mean of 140.6 and a standard deviation of 2.8. The alternative is going to be that it does not. The data does not follow a normal distribution. Okay, so we've done that. We need to find the p-value of this test. Now, at the moment, these are our observed values, and we need to know what our expected values are. Now, often with these longer type questions, you've usually done some of it in the previous part of the question. So these two values here are two of our expected values. So from 135 to 140, we would expect 314. And from 140 to 145, we would expect 421. But what's missing is less than 135 and more than 145. But the good news is that we also did something with this earlier. So we worked out that the probability of it being less than 135 was 0.0228. So for our expected value, we need to do 0.0228 multiplied by that 800 again. And for our more than 145, take that 0.0580 and multiply that by 800. So let's add those last two values into our expected column. Okay, so and I've still got them up here saved on my calculator somewhere, so I might as well use them. Let's copy that one. And paste times 800. 18.2, we're going to round that to 18. And then the last one was 0.05, that one there. And times that by 800. I can't recommend you going back and using the unrounded versions of your answers when you're going to use the number in another calculation. So 46.4, we're going to say that's 46. All right, so we're finally in a position where we can do our test. So we're going to go back to our spreadsheet now. And in my spreadsheet, I am going to use this. Should I delete all of these? Or I could. I'll tell you what I will do is I will do a new one because it might be a little bit too long for me to delete all of those numbers. So I'm just going to do a new list in spreadsheets. And I'm going to go with the same labels I had before of observed and expected. So O and expected. And what I need is my observed values. So these are the ones that we've got here, 27, 306, 413, 54. And expected 18, 314, 421, and 46. Okay, we're ready to do our tests. So in a normal calculator, statistics, stats test, goodness of fit. Okay, we've got our observed list, our expected list, and our degrees of freedom. So we've got 4 different rows here, 4 columns. So 4 minus 1, 3 degrees of freedom. I'm going to hit that enter. Okie dokie. So let's have a look. We are doing, oh no, I need to go back to my calculator. We're doing this at a 5% level. P-value is 0.100 to 3 significant figures and 0.05 for our significance level. So we're still bigger. 0.1 is bigger than 0.05. There's not enough evidence. Do you see how I'm using the same wording each time to reject H0? So what does that mean in our context? Is that this data follows a normal distribution. With a mean of 140.6 and standard deviation of 2.8. Now, I appreciate that that is a long, good 16-mark question. You could be spending 20 minutes doing that question. But they really are setting us up for success here by, in these top parts of the questions, getting us to do things that will help us with our observed and expected values. I don't think I've ever seen a question where you haven't been asked to find a probability that then isn't used later on to find the expected values. And that's probably going to be the same with this last question. Okay, so on to our last one. The last one is the binomial distribution. So what's the key things here to remember is that binomial is discrete. e.g. it means that it takes on specific values, e.g. number of pets or siblings. You can't have 3.5 pets, you can't have 7.83 siblings. And when we write binomial, we say binomial distributed, and it's n and p, where n is the number of things and p is the probability of success. Okay, so what have we got here? We've got a video game has 3 boss battles, and 1,000 people try the stage of the video game, and the number of bosses defeated by each player is recorded. So they either defeat 0 bosses, 1, 2, or 3. A chi-square goodness of fit test at the 5% significance level is used and can be modeled by a binomial distribution with a 20% probability of success. Okay, so the null and alternative hypotheses. Well, the null is always that it does fit the distribution. So the data follows a binomial distribution. Hang on. So how many bosses are there in total? There's 3 different bosses, and the probability of success is 0.2. And then our alternative is that it doesn't. The data does not follow a binomial distribution. Okay, so just like before, we're going to have to work out some probabilities so that we can do our expected values and our observed values. These are our observed values up here. Okay, so like I said before, they're going to help us here. They're going to set us up with success. So assuming the binomial distribution holds of 3 bosses and each has got a 20% chance of success, find the expected number of people that would defeat exactly 1 boss. So first of all, we're going to need to use that formula, n times p. N times p. Now, how many people are there in total? We've been told that there is 1,000 people trying this video game out. So what's our probability going to be? We want to know, what is the probability that someone defeats exactly 1 boss? Now, this is going to be using the binomial, and we need to decide that language there, exactly 1 boss, whether or not that is binomial PDF or CDF. So because it says exactly, it's not like 1 or less or 2 or more bosses. I know that that's going to be binomial CDF. Sorry, PDF. I like to think about P meaning particular. So it takes on a specific particular value. So let's work that out using our calculator. Okay, so I would like to go to statistics, distributions, binomial PDF, and my X value is 1 boss. Oh, I've chosen the wrong one. I've chosen normal. Okay, excuse me. Statistics, distributions, binomial PDF. There we go. Number of trials. There are 3 bosses. Chance of success is 0.2. And I want to know what's the probability of defeating exactly 1 boss. That is 0.384. So the probability of defeating exactly 1 boss is 0.384. So how many people in 1,000 people, how many I would expect to calculate to defeat exactly 1 boss? Well, I take 1,000 and multiply it by my answer, so 0.384. So here I can type in times 1,000. So 384. I would expect 384 people So what I'm starting to do here is I'm starting to build up that table of observed versus expected. Now, our observed, we've got they either defeat 0 bosses, 1, 2, or 3. Now, we observed 490, 384, 111, and 15. And we've just worked out we would expect 384. Oh, that's kind of cool. So it matches up exactly. But you can see that we've got 3 more of these to do if we're going to do this chi-square goodness of fit test. So let's quickly go through these now. We're going to work out the probability of 0 bosses, 1 bosses, 3 bosses, and then we're going to multiply it by 1,000 for each one. So probability that x is 0, probability that x is 2 bosses, and the probability that x is 3 bosses. Let's find out those quickly. So statistics, distributions, binomial PDF, 3 bosses, 0.2 chance of success. So what's the chance that you defeat no bosses? That's going to be 0.512. 2 bosses. I wonder if I can go back and copy this. Paste. Oh, I can. I'm going to go back and just type in 2 bosses. 0.096. And let me copy that one more time. Nice little time save here. What's the chance that I beat 3 bosses? 0.008. Okay, so to find the expected values, I'm going to need to multiply all of these by 1,000. So 0.512 times 1,000 is 512. That's my expected value. 0.096 times 1,000 is going to be 96. And that last one, 0.008 times 1,000 is going to be 8. And then I've got my table as I did before for this data here. Now I've got my observed and expected values for this problem. Okay, so let's type these in. I'm going to use the same one, just go over the top here. So I've got 490, 384, 111, and 15. I don't think there are any values below, so it works out perfectly. 512, 384, and 8. And then we can do our chi-squared goodness of fit test. So back into my just standard calculator. I'm going to go to statistics, stats tests, chi-squared goodness of fit test. My observed list is called O. This one's called E. And then my degrees of freedom, well, I've got 4 rows. So 4 minus 1 is 3. And hit enter. Okay, so degrees of freedom was 3. The p-value is 0.0242. Oh, and finally, we were doing this at a 5% level. We've finally got something, 0.0242, that is less than 0.05. So in this case, we are going to finally reject. There is enough evidence to reject H0. And what does that mean in our situation? We're going to go back to our things up here, that this data does not follow the binomial distribution. Okay, and then that's question finished. So what we've done is we've covered all of the different types of hypothesis tests. What I would encourage you to do is I'm going to post this with my notes on. I would encourage you to have a look at the questions at the bottom here. Now, the key thing for being successful in this in your exam is being able to spot the different types of questions and know when you're looking at the question what type of question it is. Is it a t-test? Is it a chi-squared independence test? Is it a goodness of fit test? So just a quick reminder at the end, chi-squared test for independence will always have a table that looks like this. The t-test usually has 2 rows of data presented like this. They don't have to be the same length. You just need to read the words and decide whether it's a two-tailed test, i.e. that the means are different, or if it's one of those ones where it's one-tailed and you think one of the groups is bigger than the other. For the goodness of fit tests, these are the difficult, often paper 2 questions. Uniform definitely could be a paper 1. And then normal and binomial tend to be longer format questions because they require you to work out probabilities as well. So in your own time, have a go at these questions. Send me an email if you want any more help with